This didactic material is meant for the personal use of the student only and is copyrighted. Its reproduction, even for a partial utilization, is strictly forbidden in compliance with and in force of the law on the author's rights.
Hello, welcome to this fourth lecture in statistics. Today we will talk about descriptive statistics. Topics: descriptive statistics, statistical hypothesis testing. And the aims of the lesson are knowing and understanding the meaning of empirical variance, standard deviation, covariance, and correlation coefficient. Knowing and applying statistical hypothesis testing in different ways. Let's start with descriptive statistics. 4.1 median quartiles. Suppose we have n observations, x1 till xn. We then define the median x 0.5 of the observations as the middle observations, and no more precisely, this expression here. Then we have, if n is odd, this expression, and if n is even, the other one. Where the observations have been sorted according to size as x1, smaller or equal x2, smaller or equal x3, till xn minus 1, smaller or equal xn. And similarly, the lower quartile, x 0.25, is defined such that 25% of the observations lie below x 0.25, and the upper quartile, x 0.75, is defined such that 75% of the observations lie below x 0.75. Then the interquartile range is the distance between this number here, and in example is this distance here, x 0.75 minus x 0.25. Then we want to introduce the mean value. As before, in the previous lecture, suppose we have n observations x1 till xn, and then we define the mean or mean value of the observations as x over sine, the sums all over the i's from 1 to n, xi, divided by n. And this is the mean value. Then we want to introduce the empirical variance and the empirical standard deviation. The empirical standard deviation is the square root of the empirical variance. Then the empirical variance is this one, as we have introduced in the previous lecture. Then we have to do to take the square root. There, the greater the empirical standard deviation S is, the more dispersed the observations are around the mean value x over sine. And this is a well-known expression here. 4.4 empirical covariance and empirical correlation coefficient. Suppose we have n pairs of observations, x1, y1, x2, y2, till xn, yn. We define the empirical covariance of these pairs as this expression here. The covariance empirical is the sum of all i's from 1 to n. This is xi minus the mean value of x times yi minus the mean value of y divided by n minus 1. Or alternatively, the empirical covariance can be computed as all the summation between xi times yi, this, minus n times the mean values of x and y, divided by n minus 1. And this is the empirical covariance. And the empirical correlation coefficient is R, sometimes the Greek letter rho is the same. This is the ratio empirical covariance divided by the empirical standard deviation of the x times the empirical standard deviation of the y, and then we can write this expression here, the empirical covariance divided by Sx times Sy, and this is the very important coefficient called correlation coefficient. The empirical correlation coefficient R always lies in this interval from -1 to 1. An understanding of the empirical correlation coefficient, if the x observations are independent of the y observations, then R will be always equal or close to 0. If the x observations and the y observations are dependent in such a way that large x values usually correspond to large y values and vice versa, then R will be equal or close to 1. Conversely, if the x observations and the y observations are dependent again in such a way that large x values usually correspond to small y values and vice versa, then R will be equal or close -1. We say that x and y are uncorrelated if the correlation coefficient is equal 0, but this is equivalently if the covariance of x and y is equal 0, because R equals 0 implies covariance. The empirical covariance must be equal 0 because this element, the denominator, must always be different from 0. A significant property of uncorrelated random variables is that the variance of x plus y must be equal the sum of the variances of x and y. This is slide 32 in lecture number 2. We saw that this also happens when the variables are independent. This is not a coincidence. Theorem. Now we have to pay attention to this theorem. If x and y are independent and the expected value of x squared and the expected value of y squared are finite, then x and y are uncorrelated. From independence of x and y, we reach the uncorrelation of x and y. And this is the proof. It suffices to prove that the expectation of x times y must be always equal the expectation of x times the expectation of y, where xi and yi are possible values of x and y, respectively. Then the possible values of x times y are given by this multiplication. xi, y, j, sorry, this is a j, where I goes from 1, 2, 3, 4, etc., and j is equal 1, 2, etc., etc. Then the expectation of x times y could be written as follows. Summation of all I and j's of this multiplication here, xi times yj, and the probability of the random variable equal x is equal the numbers of xi, and the random variable y must be equal the yj's. Then we know that this is equal by independence, because we have supposed that x and y are independent. By independence, we can always write the probability of x equal xi multiplied by probability of y equal yj, and this is the summation of all these multiplications. Then we can split the sum, and then we have sum of all I, xi probability of the random variable x equal these values xi times the summation of all j, yj times the probability that the random variable must be equal yj, but this expression is the expectation of x, and this expression here is the expectation of y. Then we have proved this statement here. Example 1, this is a very important example because it's a counterexample. Sadly, it is only too common that people sometimes think that the converse of the previous theorem is also true. We have proven, that if we have x and y independent, then we reach the uncorrelation between x and y. But if we come from the uncorrelation, it's not true that x and y are independent. This is the vice versa of this theorem here, theorem 4.1. And this is our counterexample. So let us dispel this with a counterexample. Let y and z be two independent random variables such that z is equal plus minus 1 with probability 1/2 each. And y is a random variable 1 or 2 with probability, these are the value 1 or 2 with probability 1/2 each. Now z takes value plus 1, minus 1 with probability 1/2, 50%, and y takes value 1 or 2 with probability 50% each. Then we define, pay attention, then we define the random variable x as the multiplication of y and z. Then I claim that x and y are uncorrelated but not independent. First, we note that x takes value plus minus 1 or plus minus 2. This is very easy because plus minus 1 times 1 or times 2, then we have all this combination. And then 4 values with probability 1/4 each. Then, therefore, the expectation must be equal 0. This is clear. Also, this multiplication, I define this multiplication, x times y, this is equal y squared times z, and the value are plus minus 1 or plus minus 4 with probability 1/4 each. And therefore again the expectation of this multiplication x times y is equal 0. Then follows that the covariance, and we know that the covariance has this expression here as introduced in the previous lecture, the covariance is equal 0. And if the covariance is 0, then x and y are uncorrelated. Then we have the uncorrelation, but they are not independent, x and y. Intuitively speaking, this is clear because the absolute value of x is y is the same. And there is one way to logically justify our claim, because the probability of this event, x equal 1, y equal 2, is obviously 0, but is different from the multiplication of both probability. Probability of x equal 1 times probability of x of y equal 2, and this is 1 over 8. Then we have proved that from uncorrelation we cannot reach the independence of two random variables. On the contrary, the theorem for 1 states that if x and y are independent, then then they are uncorrelated. The vice versa is not true. And these are a very easy example to prove this important statement. Okay. Then for point 5, correlation and the linear dependence. Observe that if y is equal a times x plus b for some non-random constants a different from 0 and b real number, then the covariance of the two random variables x and y is properties of the covariance is a times the covariance x, that is equal a, the variance of x, according to this expression here. And furthermore, the variance of y is a squared times the variance of x. This can be easily checked and proved. Therefore, the correlation coefficient of x and y, or rho x of y is the same, is always equal this ratio, a divided by the absolute value of a, which equals 1 if a is bigger 0, obviously. This is always positive, and rho is equal, depends on the value of a. If a is bigger than 0, then we have 1, r is equal 1, and if a is smaller than 0, then we have minus 1. In other words, if y follows x linearly, this is like the equation of a straight line. Okay, this time we use random variable, but if we think about geometry, this is equation of a straight line, and this is and then y depend on the value of x. In other words, if y follows x linearly and goes up, when x does, then its correlation to x must be plus 1. It follows x linearly but goes down. When x goes down, then its correlation must be equal minus 1. The converse is in fact true, as we have just seen in the 8th slide. Then we have another theorem. Theorem 4.2. Assume known of x and y is constant. In example, the variance of x bigger than 0 and the variance of y is bigger than 0. If the correlation coefficient of x and y is equal 1, then there exists a constant b and a bigger than 0 such that the probability of this kind of event, y equal a times x plus b, is 1. Similarly, if r, the correlation coefficient of x and y, is equal minus 1, then there exists constant b and a smaller than 0 such that the probability of y equal a times x plus b is equal 1 again. The proof. Let a be, a is a number. The number, and this number is either bigger than 0 or smaller than 0. A, just we want to choose that a is the ratio covariance of x and y and divided by the variance of x. Note that a has the sign as the correlation. This is clear. And recalling that the correlation is 1 means that the covariance of x and y squared is the variance of x times the variance of y. This is very easy if I do some calculation. Then we have the variance of y minus a times x must be equal the variance of y plus the variance of minus a times x plus 2 times the covariance of a times x minus a times x y, and this is equal variance of y, and this variance here is just a squared times variance of x minus 2 times a covariance of x and y. This is again variance of y, and this is just this ratio here, the covariance x and y squared divided by the variance of x, and this is clear equal 0. Just simply calculation. It's not very hard to do and to understand. We know that this implies that the existence of the constant r of a, the existence of a constant p such that this holds. And the proof now is completed. Now we want to consider the function depending on a and b, and this function is the expectation of y minus a times x minus b squared. We want to write this expectation as this expression here. This is property of the expectation function. This is expectation of x squared times a squared plus, this is a number, b squared, plus 2 times ab expectation of x, it's clear, minus 2 times the expectation of x times y, this here, and a, clear, and then minus 2 times the expectation of y times b plus the expectation of y squared. We have just used the expectations property. And this kind of expression represents how far is y from the line a times x plus b. Then y and x are close or not. It depends from this expression here. Using some elementary calculus, one can find that the optimal, it depends clearly from the choice of a and b. This function here depends very, very closely from a and b. And using some elementary calculus, one can find that the optimal a and b that minimize f. Minimizing f meaning that y close and closer, more close possible to the straight line a times x plus b, are the solution to the following systems of equation. And the equation are the expectation must be equal 0, a expectation of x squared times a, the expectation of x times b minus the multiplication of the x and y. This must be equal 0, and the other expression is here. I want to divide this expression here in in a system of equations, then we have this expression here, the variance, plus the multiplication of the expectation of x and y, minus the expectation of x squared times a, minus the expectation of x times y, this 0, and the fourth expression is again this one. This is a system of equation. Then we want to find b in terms of a from the second equation and plugging back in the first one, and one gets, again, a is the covariance, this ratio here, covariance of x and y, divided by the variance of x. And b must be equal this difference, the expectation of y minus expectation of x times a. These are the best choice of a and b to minimize f, making y as close as possible to the straight line a times x plus b. Now we want to plug in back into f, and then f, the function here, this function here, fab, becomes just plugging back this expression here, the expectation of this difference minus the expectation of this difference squared. Then we want to do this, the square, and then we obtain the variance at the end of this calculation. This is the variance y times 1 minus the correlation coefficients between x and y squared. So the closer absolute value of the correlation is to 1, the closer y is to being a linear function of x. There is a relation between x and y, and it depends from this expression here. So the closer the absolute value is to 1, then closer y is to being a linear function of our x. Then we want to introduce a statistical hypothesis testing. Maybe this is the most important concept in all the statistics. Then we want to talk about null hypothesis and alternative hypothesis. Then we introduce a statistical test. A statistical test is a procedure that leads to either acceptance or rejection of a null hypothesis H0 given in advance. Sometimes H0 is tested against an explicit alternative hypothesis called H1. At the base of the test lie one or more observations. The null hypothesis and the alternative hypothesis, if any, concern the question which distribution these observations were taken from. This is the problem. Then we want to introduce the significance probability and significance level. One computes the significance probability P, that is the probability if the null hypothesis H0 is true, of obtaining an observation which is as extreme or more extreme than the one given. The smaller p is, the less plausible H0 is. Often one chooses a significance level alpha, this is alpha, in advance, and typically alpha is 5%. In most of the problems, statistical problems, the significance level will be chosen as 5%. One then rejects the null hypothesis H0 if P is smaller than alpha. And one says H0 is rejected at significance level alpha. If P is greater than alpha, then H0, the null hypothesis, is accepted. And one says H0 is accepted at significance level alpha, or, equivalently, H0 cannot be rejected at the significance level alpha. We will see all these situations in a couple of examples. Then we want to introduce errors of type 1 and type 2. Then we speak about a type 1 error if we reject a true null hypothesis. If the significance level is alpha, then the risk of type 1 error is at most alpha. And then we speak about a type 2 error if we accept a false null hypothesis. The strength of a test is the probability of rejection or rejecting a false H0. The greater the strength, the smaller the risk of type 2 error. Type 2 error if we accept a false null hypothesis. Thus, the strength should be as great as possible. And this is clear. Then example 2, very easy example. Suppose we wish to investigate whether a certain dice is fair. Then by fair we here only understand the probability P of a 6 is obviously 1 over 6. Then we test the null hypothesis. H0, P is equal 1 over 6. The dice is fair. This is our null hypothesis. Against the alternative hypothesis, H1, the probability is bigger than 1 over 6, and the dice must be biased. The observations on which the test is carried out are the following 10 throws of the dice. Then the outcomes are 2, 6, 3, 6, 5, 2, 6, 6, 5, 4, 6. No, it's just a little bit strange because 1, 2, 3, 4, 5, 6. Okay. Let us in advance agree upon a significance level as before alpha is 5%. Now, by the significance probability P can be computed. By extreme observations is understood that there are many sixes. Many sixes. And we have thrown the dice 10 times. Not so much, 10 times. Okay, by extreme observation is understood that there are many sixes. Thus, P is the probability of having at least 5 sixes in 10 throws with a fair dice. Then we compute using binomial distribution and pay attention to have at least 5 sixes in 10 throws. As before, here. This is the observed value. And then using binomial distribution and using the formula, this is the summation of all k from 5 to 10, 10 over k, 1 over 6 to the k. This is the probability of having a 6, and this is the probability of not having a 6. 5 over 6 to the 10 minus k. this is our result. It can be very, very easy to compute this. When I can do the summation using simple calculation or using table. And we obtain 0.015. This is 1.5% using binomial distribution. Since P equal 1.5% is smaller than 5%, we can easily reject H0. The null hypothesis is rejected. This dice is fair. Intuitively, just seeing the outcomes, I can say it's not very, very simple to obtain these outcomes. 10 throws of the dice, the outcomes are 5, 6, or 1, 2, 3, 4, 5, 6. Using the null hypothesis testing and the alternative hypothesis testing, I can reach the result that we reject the null hypothesis. If the same test was performed with a fair dice, the probability of committing a type 1 error would be this probability here, 1.5%. Then another example, example 3. An insurance company is reviewing its current policy rates. When originally setting the rates, they believed that the average claim amount was 1,800 euros. They are concerned that the true mean is actually higher than this, because they would potentially lose a lot of money. Okay. They randomly select 40 claims and calculate a sample mean of 1,950 euros. Assuming that the standard deviation of claims is 500 euros and set again alpha equals 0.055%, test to see if the insurance company should be concerned with these numbers. Step 1, we set the null and alternative hypothesis. The null hypothesis H0 is that the mean value is smaller or equal 1,800. And the alternative hypothesis H1 is mu is bigger than 1,800. Then step 2, we want to calculate the statistic or test statistic. And using the number Z is defined, the mean value x, the mean x over sign minus mu 0, this is mu 0, divide by the sigma over square root of n, then we obtain these numbers, and this number gives this outcome, 1.897. Step 3, we want to set a rejection region. Looking at the figure in the next slide, we need to put all of alpha in the right tail. Like here, this is our bell curve, this is our random variable z, must be bigger than this region. This region had this number, 1.96. This is the 5% region, and then we conclude, we see that 1.8897 is smaller than this number, giving this region here. This is the significance level here. And therefore we fail to reject the null hypothesis. And we cannot conclude anything statistically significant from this test. I cannot tell the insurance whether or not to be concerned about their current policies. With this number here, with other numbers, we can maybe conclude that the insurance company should be concerned, but with this number and using this null hypothesis and this alternative hypothesis, we cannot tell the insurance whether or not to be concerned. Then another example, example 4. We have a sample of 40 sales receipts from a grocery store, has X oversigned 137 euro, and sigma is 30.2 euros. Use these values to test whether or not the mean sales at the grocery store are different from 150 euros. And again, as the previous example, we have step 1, set the null and alternative hypothesis. The null hypothesis H0 is given by mu equal 150. The alternative hypothesis H1 is given by mu different from 150 euros. Then we calculate the test statistic. That is again said. This is the mean minus mu 0 divided by sigma divided by square root of n. Then we obtain this number here, minus 2.722. Then we have to set the rejection region. Looking at the figure below, we need to put half of alpha in the left tail, because number here, oh, sorry, okay. Then we have to pay attention to this number here. This is a negative number. This is the left tail on the figure here. This is our 5% left tail. This is the 5% left tail. And then, if we take a look at the figure below, we need to put half of alpha in the left tail and the other half of alpha in the right tail. Thus, the absolute value for our random variable is always bigger than 2.58. This is the significance barrier level here. And step, we conclude, then we can see that this absolute value is equal to this one. This is bigger the significance value, 2.58. Thus, our test statistic is in the rejection region. Therefore, we reject the null hypothesis in favor of the alternative. And we can conclude that the mean is significantly different from 150. Thus, we have proven that the mean sales at the grocery store is not 150 euros. This is another very easy example using statistical hypothesis testing. And finally, example 5, another easy example, trying to encourage people to stop driving to the campus. The university claims that on average it takes people 30 minutes to find a parking space on campus. I don't think it takes so long to find a spot. In fact, I have a sample of the last 5 times I drove to campus, and I calculate a mean of 20. Assuming that the time it takes to find a parking spot is normal and that sigma is equal 6 minutes, then perform a hypothesis test with level alpha 0.10 to see if my claims is correct. Then, again, step 1. Set the null and the alternative hypothesis. The null hypothesis is given by mu bigger or equal 30. The alternative hypothesis, H1 mu, is smaller than 30. And want to remember that the university claims that on average it takes people 30 minutes to find the parking, but I don't think it takes so long to find a spot. Okay, H0, H1 are both given. And then we step 2, we calculate the test statistic using these elements, this number. Again, this is the formula. Then we put the numbers in the formula, and then we obtain minus 3.727. Then step 3, set rejection region. Looking at the figure below, we need to pull all of alpha in the left tail, because I claim mu is smaller than 30 minutes. Then this is the region 0.10, 10%. This is the barrier. The barrier is the significance point. This is minus 1.28. And we can conclude, we can easily see that minus 3, our outcome, minus 3.727 is smaller than minus 1.28. Thus, our test statistic is in the rejection region. Therefore, we reject the null hypothesis in favor of the alternative. The hypothesis of the university hypothesis, the first one, and the second one is my hypothesis. We can conclude that the mean is significantly less than 30 minutes in this case. Thus, I have proven that the mean time to find a parking space is less than 30 minutes. Conclusions. At the end of these lessons, the student know and master the fundamental concepts of mean value, empirical covariance, empirical correlation coefficient, using theorems and examples. He is able to apply the statistical hypothesis testing using simply examples. Thank you very much for your attention and patience. See you next lecture. Bye-bye.